The last one we're going to do, it's basically called nuclear physics. And there will be a definite question of this as the last one. So I highly recommend that you people basically, yeah, all right, let's start. So in nuclear physics, the first thing I would like to tell you is about the alpha scattering experiment, right? So alpha scattering experiment was done in a chamber which was evacuated, and they were like, there was an
Sir,
alpha
you're mute.
particle. Oh, my bad. Okay, alpha particle emitter was there in an evacuated chamber, and a thin gold foil was placed like that. All right, so what they observed was that, unfortunately, we might have to, I did not charge it and there's no electricity. Why? I hope it runs for 1 hour. Wait a second, please. So the alpha particles were targeted onto the gold foil, and what was seen that very few, like many, like almost all of them, either went straight or at very small degrees, like 10-degree deflection. Some of them deflected at large angles, and very few of them went backwards. So this was basically the experiment. So if you don't know, alpha particle is a positive, it has a positive 2 charge on it. We're going to study about it in a bit. So the experiment was carried out by two students of Rutherford, CAIE and Marston, and the conclusions of the experiment was given by Rutherford himself. So people remember this experiment with either these names. Now, so in the first part where they observed that 0 to 10 degrees, so they observed that most of the alpha particles went undeflected or at a small angle. All right, so they were like this. Now, in fact, I should have written or deflected at a very small angles. All right, so then they concluded for the observation for 10 degrees to 90 degrees there were large deflections. So they said some of the alpha particles deflected at large angles. Now, in the original experiment, there were like 8,000 alpha particles, emitted. Out of 8,000, 7 or 8 deflected at large angles. You got to remember that, all right? So they were this small number. And finally, those that went back like 90 degrees to 180 degrees, very few particles went back. And they were like in a 8,000 incident particles, only 1 or 2 managed to go back. Okay. Now, so the Rutherford gave the conclusion of why this is happening, because he said that most of the atom consists of empty space, which means there's nothing. And that's kind of true, because in today's like atom that we know, there is a second please. So basically what we know is that now this whole space, which is this one, there's nothing here, only mass at the center. So most of the particles, there's so much space that the particles that basically were not near the nucleus, they just went straight. There was no stopping there. All right, some of them, like if they got like a bit closer, so to the nucleus, right? So because of the force of repulsion, they were deflected at small angles like this, right? Like that. Then he said that for the reason why there were very like some particles deflected large angles, because he said that all the positive charge, at that time they did not know that electrons exist inside, but all the positive charge is concentrated at the center of atom, right? So which means that the particles which got really close to the nucleus, they were deflected at large angles like this, all right? Then for the ones that went back, he said that almost all the mass of an atom is concentrated in a tiny nucleus. Now writing this word tiny is very, very important, because tiny basically tells us that the nucleus is so small that only very, very few particles basically manage to come directly in front of the nucleus, and then they had to go back because of the great repulsive force. Is that clear, everyone? If you have any questions, do let me know.
Can you show the diagram again?
Yes, why not? Here it is.
Okay, thank you.
All right, Aisha, Khadija, you guys also understand this? Okay. Now, for the estimation question, we have certain things that you should remember. For the first one, we should know that the radius of proton or a neutron is about 10 raised to power minus 15 meters. Now, the other thing you should remember is that the radius of nucleus is almost the same, 10 raised to 14 to 10 raised to power minus 15. Usually it is taken as 10 raised to minus 15, so you should remember that. And then the third thing you should always remember is that the radius of atom is about 10 raised to minus 10. So this is why, like, atom is like 100,000 times greater than a nucleus. All right, now speaking of this, then just remember, write a note here, which is very important. And in an MCQ, if they ask you, you should remember that alpha scattering experiment never found out about neutrons. Neutrons were basically found much later by some other scientists, Irene and Chadwick, but right now you should remember, if they try to trick you into this, you should always remember the neutrons were not found then. Now, in today's atomic, the whole structure that we have, so in the periodic table, when you see some element, it has two values written on it. There's a value A and there's a value Z. So the value A on the top of it, this is basically called the atomic mass, and atomic mass is also known as the nucleon number. Nucleon number means how many protons and neutrons there are in the nucleus, and this is the atomic number. And atomic number basically is the proton number. So this is proton plus neutron, that is proton. You should know that if you do not take chemistry. Then now, for example, if you look at carbon, carbon is 12 and 6. Now what does these number really mean? 12 basically has in alphabet U written in front of it and E here. So this U and E has its value, like these are relative mass and relative charge. So one U is called the unified atomic mass, which is basically equal to 1.66 times 10 raised to power minus 27 kilograms. Just to manage numbers, we have created a mass. In A2 you learn why this specific number, not anything else, but for now you should remember this. This is also given in the data sheet, but it's good to remember. 1E is the elementary charge, and that means it is equivalent to 1.6 times 10 raised to minus 19 coulombs. So this is the value of one elementary charge. Now, for example, when they say that find the charge and mass of oxygen 16, all right, in SI units. So what you're going to do is you're going to say that oxygen 16 as a proton number is 8. This means that it is the mass of the oxygen atom is 16U nucleus really. So it means that 16 times 1.66 times 10 raised to power minus 27 kgs. Replace U. So this will be a total of 2.66 times 10 raised to power minus 26 kgs. So you should remember that. Okay. Now for the charge, it is basically 8E, which means 8 times the value of E is 1.6 times 10 raised to minus 19. So the charge on an oxygen nucleus is 1.28 times 10 raised to power minus 18 coulombs. Is that clear? Any questions? Please let me know. Oh crap. Our class is going to get, ruined because of this. Anyway, now one of the questions that appeared a couple of years ago is that they said estimate the density of hydrogen nucleus like this, right? Now, because you should remember density has the same formula. The density is given by mass over volume. So right now the mass of hydrogen is 1U, which is equivalent to 1.66 times 10 raised to minus 27. And the volume, because we know that hydrogen nucleus contains only a proton, so the radius of nucleus, we should remember, is 10 raised to minus 15 meter. If you don't, that you will be in trouble, which means that the volume, because it's considered sphere, is 4 by 3 pi r cube. So 4 by 3 pi 10 raised to minus 15 cube. So now to find the density, you're going to do mass over volume. So mass is 1.66 times 10 raised to minus 27 divided by 4 by 3 pi 10 raised to minus 15 cube. So when you do that, the density is going to be 3.98 times 10 raised to power 17 kg per meter cube. If you have any questions about this, please let me know. All right, is it clear, everyone? So just to show this question that this is how estimation would be done. Aman, why are you always late? Why?
Sorry, sir. I thought you'd not be taking class from 25th. Turns out it's 27th.
Aman, that is for A2 only. We finished that, right?
Yeah,
Not this.
I thought so.
Okay. Now, so this is how you would. The thing is, you should just remember the radius. And if you don't remember the radius, you'll be stuck in this question, and then you won't be able to complete it at all. Okay. With 5% battery, giving me very, very, anyway, doesn't matter. let's go forward. The next thing is the easiest thing, and that is the definition of an isotope. So who knows the definition of isotope in this class? Please don't say you guys don't know.
Different number of neutrons.
Same number
Same
of
number.
protons, different number of neutrons.
Thank God. Atoms of same element with different number of neutrons but same number of protons. Very good. Now, so for example, usually in our course we'll be using like carbon 12 is an isotope, which is the most stable one that's on the periodic table. Then carbon 13 is a one, carbon 14 is a radioactive isotope as well. So the only difference between them is that they all have 6 protons, but this has 6 neutrons, this has 7 neutrons, this is 8 neutrons. So these are all isotopes. We should just look at them by the atomic number. Now, all this, universe and the particles in it, everything is governed by 4 fundamental forces. All right. So the 4 fundamental forces in the world that exist are: number 1, the gravitational force. Then you have electrostatic force. Then you have weak nuclear force. Sometimes people also call it interaction. That's also there. And the 4th one is the strong nuclear force. These 2 forces that you see here, we're going to do them in A2, but for now we will look at them. All right, the other 2. So the weak nuclear interaction is basically responsible for beta particle radiation. We just need to remember that. And strong nuclear force is responsible. It holds the nucleus together. This is just a extra knowledge for you, that magnitude wise, right, this force is strongest amongst other fundamental. Like if this force exists, then other forces have like very, very small effect on anything. So you guys need to remember that. All right. If you have any questions, please let me know. Okay. For some reason, I feel like Essen. Who's Essen? Essen, do I know you? Acha, okay, fine. So, comparing this, I'm very happy. Okay, it's 2% only. Never mind. So, I was supposed to do type of radiations. Let's make a table and let's try to finish it before the iPad holds no more. So types of radiations, we have 3 different types that we're going to study. We're going to study about alpha particles, we're going to study about beta particles, and we're going to study about gamma. All right. Also, we are gonna look at their symbols, we are gonna look at their type, we're gonna check their relative mass, and then we're going to talk about their relative charge. We are also going to talk about their penetration. We're going to talk about their ionization. So you can also make a table on your copies, right? And then we're going to talk about their range, and then we're going to talk about their speed in air. So these things are important for us to remember. All right, make the table, and then hopefully in the next class we're gonna continue this. I'm really sorry, unexpectedly the electricity is not here and I did not charge the iPad. Okay.